Welcome to this presentation. Today we are starting a series of questions of thermochemistry. We are dealing with questions and answers. Last time, remember, we ended our presentation on question 36. Today we are starting on question 37. That question is having a series of questions, and the first sub-question is saying to explain why gas system is composed of more complex molecules, so more complex molecules, more atoms, have more internal energy, have more molar specific heat than less complex system. Here we need to explain why complex molecule having more atom are having more internal energy, more specific heats as compared to the molecule with less number of atoms. The second sub-question is asking what is the degree of freedom for monoatomic, diatomic, and polyatomic molecules. Here we need to indicate what is the number of degree of freedom for monoatomic, diatomic, and polyatomic molecules. Another sub-question is asking what is the relationship between the degree of freedom and internal energy. What is the relationship between the degree of freedom and the internal energy? The next sub-question is asking what is the relationship between the degree of freedom with CV and CP. We need to explain the relationship between the degree of freedom and the heat capacity at constant volume and the heat capacity at the constant pressure. Then you have the last sub-question is asking what is the relationship between the degree of freedom and the gamma ratio. So we need also to explain the relationship between the degree of freedom and the gamma ratio. So which is the ratio between the CP and the CV. Let's start with the answers. We need to first explain why complex molecules are having more internal energy and more molar heat capacity as compared to the molecule with less number of atom or less complex system. To understand this, we need to understand what is the kinetic energy. Remember, kinetic energy is the energy due to movement. That means it is due to the movement of more molecules and the movement of atoms. Then, in that case, we need to explain why monoatomic, diatomic molecules and polyatomic molecules have more internal energy. That means they have more movement. Let's see, for example, in monoatomic molecules, we have three different ways in which they can translate or they can move. They can move in X, Y, and Z direction. So that means the three types of movement. They can move in X, they can move in Y, and they can move in Z through translation. Translation means moving from one position to another, so they can move through X, Y, and Z. The diatomic molecule also can do the same, and polyatomic molecule they can also do the same. That means all molecules they can have three translation ways. They can have translation on X, translation on Y, and translation on the Z axis. On the other hand, then for the diatomic and polyatomic, so they have other movement apart from the translation. They can also rotate and they can vibrate. So that means when you have more movement, when you have more motions, you have more kinetic energy. That means that here for complex molecules having more atoms, they have extra motions because they have to rotate. They have also to vibrate. So that means they have more kinetic energy because they have more movements. They have the translation motion, they have rotation motion, and vibration motion. While for the monoatomic molecules or less complex molecules, they can only have translation motion, not rotation and vibration motions. For example, if you have the monoatomic gas, like for example helium, when we are talking monoatomic gas, we are talking a molecule composed of only one atom. So monoatomic gas, for example, we have the helium, so it can have a translation. It can move through Y, it can move through X, it can move through Z. But if you check for the diatomic molecule, it can also move through X, it can move through Y, it can move through Z, but it has also the rotation. It might also rotate on the axis. It might rotate on the Z axis. It might also rotate on the Y axis. So more motion. And for the triatomic gas, like water molecules and like carbon dioxide, they can also have the translation on X. They can move through X, through Y, and through Z. It can move in 3 directions, through Y, through X, and through Z. And also they can rotate on the or the axis. They can rotate on X, they can rotate on Y, and they can rotate on Z. So here also we have the carbon dioxide. It's also possible that carbon dioxide can move in X, can move in Y, can move in Z, but can also have the rotation on the Z and the Y axis. So you can see as you are increasing the number of atoms, as you are moving from the simple molecule to complex molecules, the movement is increasing and the kinetic energy is also increasing. And this movement depends on temperature. So at low temperature only you will have the translation, but as long as you are increasing the temperature, that means you have more motion. So you can see the molecules, they rotate. When you are increasing the temperature, you have a collision between molecules, and also the molecules can rotate and they can vibrate. And the vibration also, once you have the more atom, that means you have more vibration, kinetic energy, and you have less atom, we have less vibration, kinetic energy, because the vibration will affect the movement of the atoms. They can also have rotation, like you can see, the rotation on the axis, but this rotation depends on the temperature. Once you are at low temperature, you don't see this vibration motion and rotation motion. But at higher temperature, that's where this motion, they are active. You can see, for example, this one, they are rotating. You can see they are rotating, and you can see also the vibration. You can rotate and vibration as you are increasing the temperature. So at temperature below about 60 Kelvin, energy of hydrogen molecule, for example, is too low for a collision to bring the rotation and the vibration motion. If you are between minus 212.15, is somewhere around, in that case, or 60 K, that or below between below and the minus 212.15 degrees Celsius, or this is the 6K and below. So that means this one and below. In that case, this energy is very low to cause the rotation and the vibration. Only the molecules, they can do the translation, but you don't have any vibration and the translation, any vibration and rotation motion. Only translation motion are the active motion. When you increase the temperature to ambient room temperature, for example, if you are between 300 Kelvin to 600 Kelvin, in that case, rotation are full active, but no vibration motion are active. So when you increase the temperature, you are increasing also more movement of the atoms. But when you are at high level of temperature, when you are around 3000 Kelvin, the vibration motion are full active. So in that case, you have at higher temperature enough, at a higher temperature of around 3000 Kelvin. In that case, you have the translations, you have rotation, and you have vibration motions. This is example apply only for the hydrogen atoms. For hydrogen atoms at 60 Kelvin, so you have only the translation motion. When you increase the temperature between 300 Kelvin to 600 Kelvin, in that case, you have the rotation motion starting, and when you reach 3000, that is where the vibration motion are full active. Let's go to the second sub-question. It was asking to explain how many degree of freedom for monoatomic, diatomic, and polyatomic molecules. Now we need to understand what is the degree of freedom. Degree of freedom means how many type of motion a molecule can do, how many translation, how many rotation, and how many vibration motion a molecule can do. That's what we call a degree of freedom. It is also the number of independent ways in which a molecule can exhibit more motion. A molecule can exhibit motion either via translation, rotation, or via vibration motion. Translation, rotation, and vibration motion are different type of motion that a molecule can do. We can also say that the degree of freedom is the total number of independent coordinates. The coordinate system, how many dependent coordinates, is it moving on x, y, and z, and how many dependent coordinates which must be known to completely specify the position of the atom. That's also what we are calling the degree of freedom. Degree of freedom is a number of way an atom can move. It's how many type an atom can do, how many type of motion an atom can do. It's also equal to the number of independent coordinates that you can use to locate the molecule. Let's see now for monoatomic, diatomic, and triatomic how this degree of freedom they are calculated. If a molecule contains any number of atoms, so the position of each atom can be defined by 3 coordinates. Each atom can be having x, y, and z coordinate. As you can see, this is here we have one atom, so total number of coordinates. This atom has x, y, and z coordinate. That means one atom has 3 coordinates, or it has 3 degrees of freedom. When you have the 2 atoms, you have total number of coordinates is equal to 6. Each atom is having its x, y, and z coordinate. This atom also is having its x, it's having y, it is having x, and z coordinates. So that means total number of 6 coordinates. When we are having the 3 atoms, that means this atom will have a 3 coordinate. This one will have a 3 coordinate to locate its location. Here also we have 3 coordinates to locate its location. That means we have a total number of coordinates which is 9 coordinates, or 9 degrees of freedom. We are talking total number of a degree of freedom. It's equal to the number of independent coordinates. Total number of coordinates I was explaining is equal to total number of degree of freedom, and is equal to the 3 times the number of atom. For example, if we have one atom, the degree of freedom will be 3 times 1, which is equal to 3 degrees of freedom, the total degree of freedom. When you have 2 atoms, it will be 3 times 2, which is equal to 6 degrees of freedom. If we have the 3 atoms, we have 3 times n, number of atoms, 3 atoms, which will have 9 degrees of freedom. 3 times the n degree of freedom, the total degree of freedom. And this total degree of freedom is a sum of translation degree of freedom, rotational degree of freedom, and vibration degree of freedom. This total number, it is including the translation degree of freedom, rotational degree of freedom, and the vibration degree of freedom. If we can start then explaining the translation of degree of freedom for monoatomic gas, this can translate x, y, and z. So that it will have 3 translation degree of freedom. What will it be for the atomic gas? For the atomic gas, or monoatomic, it will be same as monoatomic. It will also have translating to x, it can move to y, it can also move to z. That means also the atomic gas will also going to have 3 translation degree of freedom. Translation means moving from one position to another. Again, for triatomic is also the same. It can move in x direction, y direction, and z direction. That means for any molecule, whether it is monoatomic, diatomic, or polyatomic, they have the same the translation degree of freedom, which are 3 translation degree of freedom. For monoatomic, we have 3 translation degree of freedom. For diatomic, we have 3 translation degree of freedom. And here, for a polyatomic, also we have the 3 translation degree of freedom. So they have the same translation degree of freedom because here the translation, they don't depend on a high amount of energy. Because only rotation and the vibration, they are the one which require a high amount of energy for the atom to do rotation or to perform the vibration. Let's see now the rotational degree of freedom, which is the degree of freedom the total, in which the molecules are rotating. A molecule should rotate only the center of its mass. If you have, for example, for one molecule, it's not possible because the center of mass is lying upon the atom. So here we should get the center of mass between 2 atoms. Then the molecule is going to rotate. The molecule should rotate in space about its center of mass. Then for monoatomic gas, they don't have the rotation because center of mass is sit directly on the atom and no rotation is possible. That means for a monoatomic gas having 1 atom, it will have only 3 translational degree of freedom and no rotational degree of freedom. It will have only translation but no rotation because the rotation is about the center of mass, and this one, the center of mass, lie on these atoms. Let's see for the other gas. For the atomic gas like hydrogen, of course, they have the center of mass, they should rotate. When we are talking about the atomic gas, we are talking about the gas composed of 2 atoms. They have 2 rotational degree of freedom. Here, the rotation on the axis, it is negligible because the atom sits on the x-axis. It can rotate on y. It can also rotate on z-axis, which means 2 rotational degree of freedom. For the atomic gas, they have 2 rotational degree of freedom. Note that the atomic gas are always linear. So let's go to the polyatomic gas. For linear triatomic, if you have the triatomic gas, because it is linear, it is sitting upon the x-axis, this one will be negligible. That means it will also rotate on the z and y axis. 2 rotational degree of freedom. That means for linear triatomic gas and polyatomic molecules, they have also 2 rotational degree of freedom. As long as they are linear, they have 2 rotational degree of freedom. Let's see when they are polyatomic or triatomic, which are not linear. Like for example, when we are talking about triatomic, we are talking atom having 3 atoms. This one have 4 atoms, it is polyatomic. So let's see there, because they don't sit linearly on one axis, then they can rotate on x, they can rotate on y, and they can rotate on z axis. They have 3 rotational degree of freedom. So as a summary for here, for monoatomic, when an atom is monoatomic, it means it will have only 3 translational degree of freedom. For the atomic molecule, they have a 3 translational degree of freedom, and they have also 2 rotational degree of freedom. That means you have 5. Then for linear triatomic and linear polyatomic, they have 2 rotational degree of freedom and 3 translational degree of freedom. That means you have also 5. For linear triatomic and polyatomic molecule, they have 3 translational degree of freedom plus 2 rotational freedom. They can also rotate on z and y. But for non-linear triatomic or non-linear polyatomic molecules, they have 3 translation degree of freedom plus 3 rotational degree of freedom. That makes 6. That means up to now, for non-linear triatomic and polyatomic molecule, they have 6 degree of freedom from translation and from rotation. While linear triatomic and linear polyatomic or any diatomic molecules, they will have 5 degree of freedom, 3 from translational degree of freedom and 2 from rotational degree of freedom. So now that means at room temperature we have only translation and rotation. We don't have the vibration degree of freedom. So if you are calculating the total, then at room temperature for monoatomic gas, they have 3 translation plus 0 rotation, only 3 total at room temperature. We have only translation and rotation. Monoatomic gas, they don't have rotation. Diatomic gas, they have 3 translation motion plus 2 rotational motion, which makes them 5. We are talking at room temperature. Then triatomic linear, they have 3 translation motion plus 2 rotational motion. We have 5. Then triatomic non-linear, they have 3 translation motion and they have 3 rotation, which is 6 because they are triatomic non-linear. Then polyatomic linear, because they are linear, they have only 2 rotational motion and 3 translational motion, which make total 5. Then polyatomic non-linear, they have 3 translation motion and 3 rotation motion, which makes total of 6. Only at room temperature we have translation and rotation. Because for vibration we need more energy so that the molecule they can vibrate. That is how it is up to now. We have the degree of freedom for monoatomic, diatomic, and triatomic, but at room temperature. So let's see now how the vibration degree of freedom are calculated. When you have the more energy, you have also the vibration. The unique way the molecule they can move relative to one another, they can vibrate relative to one another. That means during vibration, the atom they stretch their bond or they bend. So we have different vibration mode. We can have symmetric stretch, as you can see in the animation. We have symmetric stretching, which is not symmetric. Another mode that we have in vibration is what you call asymmetric stretch. As you can see, the stretch which is not symmetric. So these are different vibration modes that the molecules they can do. We have also another vibration mode that we call the scissoring or bending. The molecule they bend. We have also another vibration mode that we call the bending. We have also another vibration mode that we call the wagging. You can see the wagging. And we have the last vibration mode, which is the twisting. So you can see how the vibration modes are occurring. We have wagging, we have twisting. We have also, you can see also the previous, also other previous mode. You can see the rocking, and you can see also the scissoring or bending. So we have different vibration modes. So these are different vibration modes that molecule they can do. We have symmetric stretching, which is not symmetric. We have asymmetric stretch, which means the stretch which is not symmetric. When it is symmetric, that means it is stretching symmetrical. When it is asymmetric, that means the stretching is not symmetric. You can see. Then we see also the scissoring, like a scissor, or bending. So they are bending like a scissor. We have also the rocking mode, vibration mode, which is rocking. So you can see rocking mode. Different vibration mode. The molecule they can perform different vibration mode. Can you see also the wagging? We have also the twisting. So this is different vibration mode that the molecule they can do, but this occurs when you have the high temperature. So when you are calculating the total vibration mode, you should count at high temperature, you should count the translation, the rotation, and the vibration modes. And remember, the total number of modes that a molecule can do is equal to 3 times n. 3 times the number of atoms, as you have seen earlier. So now, how do you calculate the vibration degree of freedom for monoatomic gas? The total number, the total modes, the total, that means this total 3n is the total including translation, vibration, and the rotation. Then to calculate the vibration, we take the total minus the translation minus the rotation. So that means for monoatomic, you have seen that we have 3 as the translation and no rotation, which is 0. So that means 3 times 1, because the monoatomic are made of 1 atoms, minus 3 minus 0. then you have 0 vibration degree of freedom. That means for monoatomic gas, they have only a translation, they don't have a rotation, and they don't have the vibration. The total number of vibration is 0. Now for the atomic, the total is 3n minus 3, remember 3 from the translation, minus 2 from the vibration, rotation. Then we are having 3n minus 5. That means 3 times 2, because n is the 2 atoms, minus 5 is equal to 1. So we have only 1 vibration for the atomic. So we have 3n, which is total, minus the translation, which is 3, minus 2, which is rotation. Remember, we have seen that the atomic atom, they have 2 rotational degree of freedom. Then here, after calculation, they will having 1 vibration degree of freedom. For triatomic linear, so we have 3n. Remember, for triatomic linear, we have seen that they have 2 rotational degree of freedom. So 3n, the total, minus the translation degree of freedom, minus rotation degree of freedom, then the remaining one will be the vibration. 3 times 3 minus 2, we get 4 vibration degree of freedom. For triatomic nonlinear, 3n minus 3, remember triatomic nonlinear or polyatomic nonlinear, we have seen that they have 3 rotational degree of freedom. So this is the total. To get the vibration, you take the total, which is 3n minus the translation minus the rotational degree of freedom, then remaining one will be 3 vibration degree of freedom. For polyatomic linear, it's the same. We obtain 3n minus 5 degree of freedom for polyatomic, because we don't know how many number of atoms. It's better to keep this formula 3n minus 5. If we have 5 atoms, we replace here. If it is 5 atoms, we replace here by 5. Polyatomic nonlinear is also the same. So here we have to look, we have 3n minus 6. The difference between polyatomic linear and the polyatomic nonlinear is that polyatomic linear has only 2 rotational degree of freedom, as you have seen, while the polyatomic nonlinear, they have 3 rotational degree of freedom. If you are doing subtraction, then you get 3n minus 6. Here you get 3n minus 5. So, as a summary, monoatomic have no vibration degree of freedom. The atomic molecule have only 1 vibration of 4 degree of freedom, which is here. Triatomic linear, they have 4 vibration degree of freedom. Triatomic nonlinear, they have 3 vibration degree of freedom. Then polyatomic linear, they have 3n minus 5 degree of freedom, and the polyatomic nonlinear, they have 3n minus 6 degree of freedom. So let's see now the total degree of freedom. So is equal to the translation plus rotation plus vibration. For monoatomic, they have 3 as total degree of freedom. For the atomic, they have 3 translation, 2 rotation, and 1 vibration. We have 6. For triatomic linear, they will have 3 translation, 2 rotation, and 4 vibration, which is equal to 9. Triatomic nonlinear, they have 3 and 3. 3 translation, 3 rotation, and 3 vibration. 9. Polyatomic linear, because they are linear, they have 2 rotation. We have 3 plus 2, 3 translation plus 2 rotation plus 3n minus 5 from the vibration, 3n. Then for polyatomic nonlinear, they have 3 translation, 3 rotation, and 3n minus 6 as the vibration. Here you have the 3n. So this is a summary of what you have seen in the table. Monoatomic gas, they have 3 translation, rotation 0, and vibration 0. Then the total will be 3n. 3 times 1 is equal to 3. Then the atomic, they have 3 translation, 2 rotation, the vibration is 1. Then the total is 3n, which is equal to 3 times 2, which is equal to 6. You can also add 3 plus 2 plus 1, which is equal to 6. Then for triatomic linear, they have 3 translation, 2 rotation, 3n minus 5 vibration. So then you have the total, which is 3n, 3 times 3 is equal to 9, 3 atoms. Here 2 atoms, here 1 atoms. You can also add here 3 plus 2 plus 4, it is equal to 9. For triatomic and non-linear, also we have 3 translation, 3 rotation, 3n minus 6 vibration, so which is equal to 3n, 3 times 3 is equal to 9. For polyatomic linear rates, for example, count for 4 atoms, we have 3 translation, 2 rotation, 3n minus 5, we are replacing 4 because we say, for example, you have 4 atoms, which is equal to 7, and here it will be 3n, 3 times 4, it will be equal to 12. You can also add 3 plus 2 plus 7, which is going to be 12. For polyatomic and non-linear, 4 atoms, they have 3 atoms here, they have, because they are non-linear, they have 3 rotation, 3n minus 6, so we have, say, for atom, 3 times 4 minus 6 is equal to 6. Then here we replace by 4 atom, 3 times 4 is equal to 12. So this is the degree of freedom for translation, rotation, and vibration. And on that, at room temperature, we count only translation and rotation at room temperature. This vibration, we are counting them at a very high temperature. What was the second sub-question? The second sub-question was asking to explain the relationship between degree of freedom and the internal energy. So we are going to assume that a molecule is moving in a cuboid in one direction. That means the molecule is having 1 degree of freedom moving in one direction, x direction. The cuboid, the length of cuboid, let's assume that the length of cuboid is L and is equal to the width. So the length, width, and the height, they will be equal in the cuboid. The atom will move from this and hit the ore and coming back. That means the atom will move the distance of 2a, distance of going back and coming back. But in one direction, that means you have seen degree of freedom is the number of independent coordinates. That means we consider that only it will move in x direction. That means we have 1 degree of freedom. It is going to collide the ore and returning back. So that's what it means. Then let's see the pressure which is exerted by the molecules. These molecules, we're going to hit the ore and coming back. Let's see the pressure that is exerted by this molecule. That the pressure exerted by the molecule will be equal to the force over the area. The force over the area. Now, what will be the force? The force is equal to the mass times the acceleration of the atoms. The area of the ore, it will be the L over L times L, which is equal to L squared. The area of the ore, because the atom will hit the ore. The pressure, then we replace the force is equal to the mass times acceleration, dividing with the area of the ore. Then acceleration, remember, it is the change in the velocity over time, but it will be the change in the velocity in the direction going to x. Remember, we have said that the atom, we consider the atom is moving only in the x direction. Pressure then, it will be equal to the mass times dv over L squared t. So here we have replaced the change in the velocity function of time. So here then, what is m times dvx is the change in momentum. Then the pressure will be equal to the change in momentum dividing with L squared t. This is L squared is this distance over t. Then the molecule will hit the ore and comes back. That means the distance that will travel, it will be twice. The molecule is going into opposite direction. The momentum then, we have the momentum of the molecule is going and the momentum of hitting back this box. So we have the momentum when the molecule is going to the ore. We have also the momentum when the molecule is returning back. So that means the momentum is equal to mvx in direction toward the ore. We have also the momentum which is equal to minus mvx in back direction after hitting the ore. Then the change in momentum, it will be dp, which is equal to mvx in the direction going to the ore minus mvx in direction back coming back from the hole. So that means the change in momentum will be equal to 2mvx. So pressure, we can then replace dP by 2mvx, which is equal to L2t. So the distance, which is the distance is equal to speed times time. This time is equal to distance over speed. So that means the time that is going to be used by the molecule to travel, it will be equal to distance over speed. So we can then replace this t by distance over speed. The molecule is going to travel a double distance. That means the distance will be to L going and back. So then you can have it is equal to L over speed. So that means the 2L is the distance. It is going to go back over this speed. Then we get the time. The pressure, we can then replace the time by its value. Here we are replacing the time by 2L over V. Then the L, the 2 they will cancel. Then 2 here we cancel. Then we get the L squared times L, which will be equal to K L cubed. So then we get this formula where mv square x over L cubed. So what is this L cubed? That is the volume of the container. So then we have mv square x. Then this is the volume. So that means L cubed is the volume of the container. Then we can have this formula where we have the pressure is equal to mv square x over the volume. You can take PV then, because we are looking for the energy which is exerted by one atom going in one direction. That means the energy is exerted by 1 degree of freedom of one atoms. This is the pressure set by one molecule on the wall in one direction, or the pressure exerted by 1 degree of freedom for one more molecules. So that means we can take PV is equal to mv square. So dividing both terms by 2, we get 1 over PV, 1 over mv square. So that means that is the kinetic energy. That is the energy exerted by 1 degree of freedom for one atom. So remember PV is equal to nRT, then we can replace PV by nRT. We get 1 over half nRT. We get this energy, the kinetic energy, exerted by 1 degree of freedom, because we are counting in one molecule, one atom going in one direction. Then we have also here 1 over 2. Remember, this number of mole is equal to the total number of atoms dividing with the Avogadro's number, 80, 1 over 2 mv squared. So we are still looking for the energy exerted by 1 degree of freedom. See here, this is the kinetic energy exerted by 1 degree of freedom. Remember, the kinetic energy is equal to the total internal energy, because we don't have the intermolecular force of attraction. The potential energy is 0. So remember, n is 1. We are counting for n is 1 molecule. So one molecule having 1 degree of freedom. So that means we have here, we are replacing with 1. Here we need to have L over degree of Avogadro's number. What is L over Avogadro's number? L over Avogadro's number. What is L over Avogadro's number? This is the Kb, the Boltzmann constant. So then we are replacing 1 over half Kbt, the Boltzmann constant times 10. That means when you have 1 degree of freedom, one molecule having 1 degree of freedom, it contributes 1 over 2 kBt to the kinetic energy, or to the total internal energy. That means kinetic energy contributed by one molecule, 1 degree of freedom, one molecule going on x direction, or 1 degree of freedom is equal to 1 over 2 kBt. So any degree of freedom contribute 1 over 2 kBt to the internal energy. A molecule moving in x, y, and z direction, that means it will have 3 degrees of freedom. We have considered only a molecule moving in x direction, but if the molecule is moving in x, y direction, it is moving in 3 direction, then it will have kinetic energy is equal to the kinetic energy in x plus kinetic energy in y, kinetic energy in z, which will be equal to the 1 over 2 kBt x plus 1 over 2 kBty plus 1 over 2 kBtz, it will also equal to the 1 over 2 mv square x plus the movement in y plus also the kinetic energy in z. So that means we have the kinetic energy or total is equal to 3 over 2 kBt. So we are adding this one, and this one is equal to 3 over 2, which is equal to 1 over 2 mv. This is the root mean square velocity. So here we are going to have the root mean square velocity. So that means the atom which is moving in x, y, and z direction, that means which if it is having the 3 translation degree of freedom, it will have 3 over 2 kBt or 1 over 2 mv root times m times v, which is the average, which is the root mean square velocity to the internal energy. That means molecules for monoatomic gas, they have internal energy is equal to 3 over 2 kBt, because monoatomic gas, they have only a movement in x, y, and z. They don't have a rotation and they don't have the vibration. They have only translation in 3 directions. That means the kinetic energy or the internal energy for a monoatomic gas will be equal to 3 over 2 kBt. So according to the law of partition of energy, what we call according to the law of equipartition of energy, the law of equipartition of energy for any diatomic system in thermal equilibrium, the total energy for the system is equally divided among the degree of freedom. So the total energy is divided among the degree of freedom, and each degree of freedom contribute 1 over 2 kBt to the internal energy. That's what the law of equipartition energy is saying. For each degree of freedom, as you have seen, it will contribute 1 over 2 kBt to the total internal energy. For f degree of freedom, if you have degree of freedom, then for one molecule, it will contribute 1 over 2 kBt times f, the total number of degree of freedom. Then if you have any molecules, if you have f degree of freedom and also you have any molecules, so it will contribute 1 over 2 kBt times the number of degree of freedom times the number of more molecules as the total energy for the internal energy. So in that case, total internal energy will be equal to 1 over 2 kBt. This is the contribution for 1 degree of freedom for 1 atoms here times the number of degree of freedom times the number of atoms. This is the total internal energy. That means the change in internal energy will be equal to 1 over half kB, the change in temperature times the number of degree of freedom times the number of particles, the number of molecules, the number of atoms for monoatomic gas. So that was the relation between the degree of freedom and the internal energy. For monoatomic gas with 3 degrees of freedom at room temperature, we have internal energy is equal to 1 over 2 kB dt times the degree of freedom is 3. So then it will have 3 over 2 n kB dt. So this n is the number of atoms or number of molecules. For then du will be equal to 3 over 2 n. This is L over Avogadro's number. We are replacing the kB, the Boltzmann constant, by its value is equal to the R, gas constant dividing Avogadro's number. Then we will get here, remember Avogadro's number is equal to the number, total number of a molecule, total number of atoms dividing with the number of moles. So here we are replacing the Avogadro's number by n over n, the total number of molecules or particles dividing with the number of moles. At the end, then we get 3 over 2 n, which is the number of particles. This one will cancel with this one, r over dt times n. So then we get the internal energy is equal to 3 over 2 n r dt. For monoatomic gas, then with 3 degrees of freedom, it has only 3 degrees of freedom because I have seen that at room temperature. For the monoatomic gas, whether you have room temperature or higher temperature, it has only 3 translation degrees of freedom. So the total number for monoatomic gas is 3 degrees of freedom. So we don't have the rotation, we don't have the vibration for a monoatomic gas. That means this is 3, this stands for the degree of freedom. As you can see in the formula, this is degree of freedom for monoatomic gas. Then for the atomic gas, we 5 degree of freedom at room temperature, because at room temperature we have only translation and rotation. We don't have the vibration. That means it has only 5 degree of freedom. In that case, at room temperature, we consider only translation and vibration and rotation, not vibration. At room temperature, we consider only translation and rotation. Vibration will come when you have the higher temperature. For the atomic gas, 5 degree of freedom at room temperature, then here we replace by 5. That means the internal energy will be equal to 5 over 2 NKB dt will be equal to 5 over 2 NR dt. So this is the relation between the degree of freedom and the internal energy. So another sub-question was asking to derive the relationship between the degree of freedom and Cp and Cv. So we know that the internal energy is equal to 1 over 2 kB dt times the degree of freedom times the number of particles, as you have seen above. So replacing this n, the number of particles is equal to the number of mole times the Avogadro's number, which is the number of molecules in 1 mole. So taking the number of mole times the number of molecules in 1 mole, then in that case we get the total number of molecules. The number of mole times the number of molecules in 1 mole, then you get the total number of molecules. So we replace also with this Kb, you can replace this Kb by L over Avogadro's number. So we replace here Avogadro's number, then it's equal to L over Kb. So Avogadro's number here, it will be equal to L over Kb. So here, this Avogadro's number can be replaced by L over Kb. After replacing, then we want to eliminate this Kb. So then, change internal is equal to 1 over Kb. Then we replace the Kb. We cancel the Kb by replacing Avogadro's number with L over Kb. So if we replace L over Kb with this Avogadro's number, then we cancel this one and this one, and cancel this one and this one, then you get this relation. So remember, the Cv is equal to the Q over N dt. The heat capacity at constant volume is equal to Q dividing with N dt. Then we can here what will be the Q. Remember, the internal energy is equal to Q plus work done. And the work done is equal to PdV, but we have a constant volume. If you have a constant volume, that means this dV is equal to 0. Q is equal to du minus PdV minus du minus 0, which is equal to du. That means this Q will be equal to du. So then you can say that Q is equal to du, which is equal to 1 over 2 F times N times RT. So this is du, is here, 1 over 2 Fn RT. Then this is also, we have there that Q is equal to du. That means du will be equal to this, and it will be equal to the Q. Then you can replace Q by its value. By du, we replace Q by its value. So then we have the Cv is equal to Q, which is equal to this one, dividing with N dt. So then, what will be equal to Cv? We have 1 over 2. So we cancel here N, they will be cancelled. The dt, they will be cancelled. We remain with L times F. 1 over 2 L times F. Then, what will be 1 over 2? We have 1 over 2 then, Kb times F times the Avogadro's number. So we are replacing the value of L. So remember, we are replacing the F, we are replacing also the L by value, because the L is equal to the Avogadro's number times the Kb. So we are here, it is coming from here. If we can have it here, remember, L is equal to the Avogadro's number, Kb is equal to L over Avogadro's number, then this Kb will be equal to L over Avogadro's number, and what will be the L? L will be equal to Kb times Avogadro's number. So we were here then. So We replace this L by Kb times Avogadro's number times F. So that means each degree of freedom contribute 1 over 2R to the heat capacity. You can see the CV is equal 1 over 2L. That means each degree of freedom contribute 1 over 2L to the heat capacity, and it contribute 1 over 2 Kb to the system heat capacity. So here, it contribute 1 over Kb to the system heat capacity. If you can see, here 1 degree of freedom will contribute 1 over 2R. Here, 1 degree of freedom, it will contribute 1 over 2 Kb times Avogadro's number. That's why we are taking it to the system heat capacity. Here, it contributes 1 over 2L to the heat capacity. It will also contribute 1 over 2 Kb to the system heat capacity. That is their relation. 1 degree of freedom contribute 1 over 2L to the heat capacity and contribute 1 over 2 Kb to the system heat capacity. Then, what is the CP? So here we derive the relation between CV and degree of freedom. Now, what will be the relationship between the degree of freedom and CP? Remember, CP is equal to CV plus L. We have derived this formula before. CV plus L. Then, that means we replace the CV by its value, 1 over 2LF. Then plus L. Then we get this one. We just put aside R, 1 over F plus 1L. That will be the CP. Then for monoatomic gas at room temperature, we have the CV, which is equal to 1 over 2 L times the degree of freedom. Remember, for atomic gas, we have 3 degrees of freedom. Then we have 3 over 2R. For monoatomic gas, CV is equal to 3 over 2R. But CP will be equal to 3 over 2R, CV plus R. That we get 5 over 2R at room temperature. We have CV is equal to 3 over 2R, and we have CP is equal to 5 over 2R. For the atomic gas at room temperature, remember they have 5 degrees of freedom. That means I will replace with 5, F by 5. CV is equal to 1 over 2L times F. We replace F by 5. Then you have 5 over 2R, and CP will be equal to 7 over 2R. 5 over 2R, taking the CP plus R, we get 7 over 2R. That is at room temperature. The next question, which the last question was asking to derive the relation between degree of freedom and the gamma ratio. Gamma ratio is the ratio between CP and CV. So here we replace the CP by the value F over 2 plus 1L, and the CV we replace F over 2L. We replace the CP by value and replace the CV by its formula. Then we will get this one, F over 2 plus 1 times 2 over F. So we are multiplying this fraction by reversing it. Then we get this one. So you get that the gamma ratio is equal to 1 plus 2F. After then, for monoatomic gas with 3 degrees of freedom at room temperature, we replace here 3 here, and we have a gamma ratio of 1.66. And for the atomic gas at room temperature, it has 5 degrees of freedom. So that means we replace here 5. So y is equal to 1 plus 2 over 5. It will have a gamma ratio of 1.4.